If you see the varistor microstructure, it consists of zinc oxide grains which are separated by intergranular boundaries. So from the zinc oxide varistor SEM micrograph, that is image, so it is clearly seen that crystalline grains are separated by intergranular boundaries, and each boundary will act as a PN junction. So when designing a varistor for a particular voltage, so the more number of the grains between the electrodes will increase the varistor voltage. So the relationship between voltage and current of a varistor can be approximated to V is equal to C into I power beta, where C is the varistor voltage at 1 ampere current, I is the actual working current. Suppose C is equal to 230 volts at 1 ampere and beta is equal to 0.035 for zinc oxide material. And for different currents, I is equal to 10 power minus 3 amps under normal operating condition and I is equal to 100 amps under transient condition. The value of V can be calculated as 180 volts and 270 volts. And it is clearly seen that in case of over voltage, so or transient, the varistor will create a short circuit path and it will produce the circuit. So the current versus voltage of the varistor so is divided into three regions, A, B, C. So A is the normal operating condition of the varistor, and in this the current drawn is very less, 10 microamps to 300 microamps, and B is the production zone. So this is the maximum voltage, that is the maximum voltage that the varistor will clamp in case of any transient, and C is the maximum peak current that the varistor can withstand once in its lifetime, that is non-repetitive surge current of the varistor. How the varistor will protect the load or a component, so it can be seen from this simple equation. So if you apply Ohm's law at the input section, VI is equal to VR plus V naught, and the voltage across the resistor is R into A, and voltage across the varistor is equal to C into I power beta. And if you see, for an increase in the voltage delta Vi, so there is an increase in current of delta I, and from the equation you can see for a small value of beta, it is evident that the modification of C into I power beta will be very small compared to the variation of R into I when Vi is increased to Vi plus delta Vi. So a large increase of Vi will induce a large increase of VR and a small increase of V naught. So this how the varistor will protect the circuit or load in case of transient or over voltage. So these are the typical applications of the varistor. If you see on the left side, so when the switch S is closed, so the inductor stores the energy, and when the switch is open, the energy that is stored in the inductor will be released as a transient, and that is spike. So and it will damage the thyristor bridge. So the varistor that is placed across the thyristor will suppress that transient and protects the bridge. And on the right side, the varistor that is placed between the line and neutral of the incoming power supply. So it will protect the power supply, that is switched mode power supply, in case of transient or over voltage. The typical specifications of the varistor are voltage rating, that is maximum voltage that may be applied continuously between the terminals of the component. And other one is varistor voltage. This is voltage across the varistor when a 1 milliampere current is passed to the component. So this is specification used for comparison between the model and types of the varistor. And next one is clamping voltage. This is maximum voltage between the terminals when a standard pulse of current with rise time of 8 microsecond and pulse width of 20 microsecond is applied through the resistor, that is for varistor. And peak surge current. This is the maximum non-repetitive current that the varistor can withstand, and this is characterized by pulse with 8 microsecond rise time and 20 microsecond pulse width. Next specification is surge current, and this is the maximum energy that the varistor can be dissipated, and this is characterized by a standard pulse of current with 10 microsecond rise time and 1000 microsecond pulse width. And next specification is capacitance, and this capacitance is value between the terminals of the varistor, and this plays a vital role when the varistors are used for the protecting the digital circuits. These are the typical electrical characteristics of the varistor. So advantage of the varistor is it is having better thermal properties, means it having greater energy handling capabilities than other transient protection devices like Zener diodes, and it is bidirectional. It is having wide voltage range, and it is having higher energy absorption capability, and is having fast response to transients, and it is low cost. So thank you for watching my video.